Afternoon, grade 11. So we're going to continue on today with our study of gases. We're going to learn a few more gas laws today, including Charles, Gay-Lussac's, and the combined gas law. Where we are in your textbook is 11.8 to 11.9, and the pages can be found right here if you need some extra help. So today we're going to be going through these three laws, the Charles law, Gay-Lussac's law, and combined gas law. We'll do some practice problems, and then you'll have a chance to review some as well from your textbook. You'll fill out your answers, you can submit them on Classroom like we've been doing, either on a Google Doc or pictures of your hard copy work if you'd prefer to do it that way. So by the end of the class, what you should be able to do is describe how temperature and volume in gases are related in terms of Charles' law and kinetic molecular theory. Describe how temperature and pressure in gases are related in terms of Gay-Lussac's law and kinetic molecular theory. Okay, so yesterday we learned about Boyle's law, where we learned P1V1 equals P2V2. Today we're going to be looking at two different variables. We're going to be looking at, instead of pressure and volume today, volume and temperature. So what we're going to be exploring today, and again with this same interactive we've looked at it yesterday, is how volume and temperature is related. So for example, what happens to the volume of a gas if I heat it up or if I cool it down, okay? Or what happens to a temperature of a gas, the pressure back up, if I decrease the volume, okay, or increase the volume. So this is summarized with a formula called V1 over T1 equals V2 over T2. So it's similar to yesterday, but instead of multiplying those two variables, we're going to be dividing them, okay? So essentially, what we're taking a look at here, and if you look at that relationship, it says as the temperature of a gas increases, the volume will increase proportionally. Now, it's different than yesterday where we said, well, if one goes up, the other's going to go down. These two are actually going to move in the same direction, okay? And again, this is just like yesterday, assuming that the pressure and the amount of gas stays the same. So when temperature increases, so will volume, which means, for example, if I double the temperature, I'm also going to double the volume, which is different than yesterday where we looked at it was an inverted relationship. If you doubled the temperature, if you doubled the pressure, you have the volume. Okay, so these move in the same direction. Temperature, oftentimes in these types of calculations, is going to be measured in something called kelvins instead of degrees Celsius or degrees Fahrenheit. This is another unit of measurement that we use to measure temperature. And what's beneficial to us in these types of calculations is it's measured from absolute zero. So absolute zero is technically negative 273.15 degrees Celsius, but what it is it's essentially where there is no more kinetic movement in the molecules. So it is so cold, even though we said yesterday, and we've learned in the particle theory of matter, that all matter, the particles are at least vibrating. It's so cold and there's so little energy available in the system, all of the particles are consistently still. The benefit of this for us in terms of our calculations is you don't have to worry about negative and positive values impacting our math and our calculations. You're always going to get a positive number because it starts at zero. Now, it is important to know how to convert between kelvins and degrees Celsius. Essentially, if you have in a question, you're given the degrees Celsius, you need to add 273.15 to it, and then that's how you convert into kelvins. Okay. So, like yesterday we said, we talked about the difference between STP and SATP, and we talked about 0 degrees Celsius versus 25 degrees Celsius. For today, because kelvins are what we're going to be using these calculations much more often, what we could say this is really 0 degrees being 273.15 Kelvin, and 25 degrees Celsius being 298.15 Kelvin. Those are saying the same things, but it's more consistent in the units that we're going to see more often in gas calculations. Okay? So I'm going to make myself disappear again, and we're going to look at some practice problems and make sure we know how to use this new formula that we learned, okay? So we're going to be using, we said, Charles' law, V1 over T1 equals V2 over T2. Okay. So this says, a gas inside a cylinder with a movable piston is heated from 25 degrees Celsius to 315 degrees Celsius. What's the new volume of the gas, knowing the initial volume was 0.3 liters? So this was my initial volume. So this is my V1. And it says it was heated from 25 degrees Celsius. So this was my initial temperature, my T1, to 315 degrees Celsius. So this is going to be my T2. Now, right away, what should stick out to us as well is this was given to us in degrees Celsius, and we need to convert those to Kelvin. Okay? So first thing I'm going to do before I even get to my formula is convert my temperatures. So I'm going to say my Kelvin is my degrees Celsius plus 273.15. So for example, 25 degrees Celsius plus 273.15 is going to give me my new temperature in kelvins. Well, it's the same temperature, it's just in a new unit. So it's going to be 298.15 Kelvin. And I'll do that for my other temperature as well. But this was 315. So this is going to give me 588.15 Kelvin. Now remember, when you're doing these calculations, it's really important that you convert your temperatures into kelvins, just like when we were doing our dilution calculations and we needed our volume in liters. Okay. So now we're going to say my V1 over T1 equals V2 over T2. Okay. So my initial volume, we said, was 0.30 liters. My initial temperature was 25 degrees Celsius, which I converted to 298.15 Kelvin. I don't know my secondary volume. That's what I'm trying to figure out. But I do know that my secondary temperature was 588.15 Kelvin. Now to get V2 by itself, I need to multiply both sides by 588. I didn't really leave myself a lot of room there. So my V2 is going to equal 588.15 Kelvin times 0.30 liters divided by 298.15 Kelvin. So that's going to give me and I'm going to report this to, if I look at my question, this has 2 significant figures, this has 3, this has 2. So I'm going to report to 2, so this is going to be 0.59 liters. Now if I think this through, we said in this case, if temperature increases, volume should also increase. So does my final answer make sense? Well, I heated it from 25 degrees Celsius to 315, so my temperature went up. And my volume went from 0.3 to almost 0.6. So yes, that follows that trend. So my answer likely is following. I didn't make any silly inversions in my math. Okay. Like yesterday, if this was a test or a quiz or an exam, you would get a mark for your formula, showing your work, including units, and final answer, including units and significant figures. Okay, let's try one more. Says a 600 milliliter sample of nitrogen is heated from 27 degrees Celsius to 77 degrees Celsius at constant pressure. What's the new volume? So we're still going to be using here V1 T1 equals V2 T2. So the sample starts off at 600 milliliters and 27 degrees Celsius. So that's my V1 and my T1. Okay. But my T2, my secondary temperature, is what it heats up to, which is 77 degrees Celsius. First thing I have to do, like before, is I have to convert my two temperatures. 27 gives me 300.15 Kelvin. Do the same thing for my 77, 273.15 needs to be added to it. Okay. Just going to give me, oops, go back. 350.15 Kelvin. Okay, that's what I'm going to plug in. I also, just from habit, would suggest you convert your volumes into liters, just because some of the questions in the future, we'll go over those in a little bit, will require volume in liters. So it may just, if you're in the habit, will prevent you from making mistakes in the future. So I'm going to put this as 6.6 liters over T1, which I just converted here, 300.15 Kelvin, which equals V2 over D2, which is 350.15 Kelvin. So to get V2 by itself, I need to divide both sides. Sorry, multiply both sides to get V2 by itself. Okay, so I can isolate for that variable. Now my temperature has increased again. So I should be expecting a volume that's bigger than 600 milliliters or 0.6 liters if I'm doing my math right. So let's see. What we get. We do get a volume that's bigger. And if I look, this is 3 significant figures. This is 2, this is 2. So I'm going to report this as 0.70 liters. Okay? Or 700 milliliters. So my temperature increased, so did my volume. So I have more confidence that what I'm doing is correct. Okay. Now, the last relationship we need to talk about is Gay-Lussac's law. This is the relationship that we observe between pressure and temperature. So if we go back to this gas law simulator, what we're going to be looking at here is what happens to the pressure if I heat up a gas or if I cool down a gas, okay? Or what happens to the temperature if I increase pressure or decrease pressure, okay? So you can play around with that interactive to help test some of the stuff we're going to be calculating today. So P1 over T1 equals P2 over T2 really means that as the temperature of a gas increases, the pressure will also increase proportionally. Now it's going to be more like Charles' law than Boyle's law in that because the variables are over one another, if one increases, the other one will increase. If one decreases, the other one will decrease, okay? So essentially in words, what we're saying is as temperature increases, so will the pressure, or if temperature is doubled, the pressure will also double, okay? So let's take a look at how we use this formula. Okay, so it says a sealed storage tank contains argon gas at 18 degrees Celsius and a pressure of 875 kilopascals. What's the new pressure of the tank if its contents are warmed to 32 degrees Celsius during the day? Okay, so we're starting off with this initial pressure and this initial temperature, and it gets heated up later in the day to this new temperature. Okay, so we're going to use P1 over T1 equals P2 over T2. Just like the previous questions, because this is given to me in degrees Celsius, I do have to convert those to kelvins. So you're going to get really good at this. Just adding 273.15 to get it into kelvins, so that it's in the right units for us. Okay, sometimes it may be given to you in kelvins, but often, just because we measure temperature more often in degrees Celsius, often you just have to do that simple calculation. Now it's just a matter of plugging those in. My initial pressure is 875 kilopascals. My initial temperature was 291.15 Kelvin. We don't know what my new pressure is, but we do know that my new temperature is 305.15 Kelvin. Now already, because it's heating up, because the temperature is going up, I should already be expecting the pressure to go up because those are going to vary together. If one doubles, the other one will double. Okay, so I should be expecting to get a number bigger than 875. Okay, so to get pressure 2 by itself, I'm going to multiply both sides by 305.15 Kelvin. So if I rearrange that equation, what we're going to get and if I look at my question, I'm going to report this to two significant figures. Both of the temperatures have 2 and the pressure has 3. So I'm going to report this to 9.2 times 10 to the 2 kilopascals, which is about 920 kilopascals, which is bigger than 875. So I can have confidence that my answer is correct, or I haven't made a silly mistake in my math. Okay, one last one. This says if a gas in a closed container is pressurized from 15 atmospheres to 16 atmospheres, what would be its original temperature was 25 degrees Celsius, what would be the final temperature? So its initial pressure was 15. It was then increased in pressure to 16, so that's my P1 and my P2. The initial temperature was 25 degrees Celsius, so that's my T1. I'm trying to figure out here what my T2 is. So I only have one temperature I need to convert. Okay. I need this to be in kelvins. Now the previous question we used kilopascals, this question we're using atmospheres. Both of those units are fine, just know whatever unit you get in is what's going to get out. So what I mean by that is because in this question my pressure was given to me in kilopascals, I knew my answer was going to be in kilopascals. If your variables are given to you in atmospheres, if you were calculating for pressure, you would be given your answer out in atmospheres. Okay, so P1 over T1 equals P2 over T2. So my initial pressure is 15 atmospheres, and my initial temperature was 298.15 Kelvin. My P2 was 16 atmospheres. I don't know what my T2 is. So T2 can't be on the bottom, so I'm going to start off by multiplying both sides by T2 to get it on the top. Okay, which now means I have to divide by 15 atmospheres to get rid of this. And I have to multiply by 298.15 kelvins to get rid of this so that T2 is by itself. So it's going to be T2 is 16 atmospheres times 298.15 Kelvin all over 15 atmospheres. So we should get a number because our pressure increased. We should expect our temperature to increase as well. So we're hoping for a number that's bigger than 298. Okay, and I'm going to report this to three significant figures. This is 3, this is 3, this is 3. So this is going to be 318 kelvins, which is good. It's bigger than 298. The temperature increased, so I can have more confidence in the answer. Now, that may seem like a lot of formulas to remember. The good news is we can just remember the combined gas law, okay? And the combined gas law is more useful anyways, because instead of just looking at how 2 of the 3 possible variables can interact, it looks at all 3. So this is actually a summary gas equation that tells us how all pressure, volume, and temperature vary together. How I used to remember this It's P1V1 over T1 equals P2V2 over T2. I used to always remember it as potatoes and vegetables on the table. Okay, come up with a little mnemonic like that. P and V are on top of T, so potatoes and vegetables are on the table. And then you'll know where each variable goes, so you won't be putting volume on the bottom by mistake. Okay, so what this equation does, which is more useful to us, is we could alter the volume and the temperature and the pressure, and we can interact all these variables, and it'll tell us what's going to happen with our gas. Okay, which is more reflective of what's going to happen in real life anyways. Good news too is if you just remember P1V1 equals P1V1 over T1, or potatoes and vegetables on the table 1 equals P2V2 over T2, or potatoes and vegetables on the table 2, you can remember all three of the previous equations, Boyle's, Charles, and Gay-Lussac's law. So for example, Boyle's law we know looks at pressure and volume and ignores temperature. So if I just ignore the T's on the combined gas law, I'm left with Boyle's law. Or we know in Charles' law, for example, it ignores pressure and just looks at volumes and temperature. Instead of having to re-memorize this formula, just disregard P, and you're left with Charles' law, V1 over T1 equals V2 over T2. In that same way, Gay-Lussac's law we know doesn't really concern itself with volume. It's pressure and temperature. So P1 over T1 equals P2 over T2. Instead of having to memorize all three of those equations, you just have the one. And if you're not using one of the variables, you ignore it. You cancel it out, and you're left with combined gas law. So let's see how we would use one of these. So this says a balloon contains hydrogen at 20 degrees Celsius and a pressure of 100 kilopascals and 7.5 liters. So this is my T1, this is my P1, and this is my V1. Calculate the new volume, so we don't know what V2 is, of the balloon after it rises to the upper atmosphere with a pressure, so this is my P2, of 28 kilopascals and a temperature, T2, of negative 36 degrees Celsius. So I'm going to set up my equation, potatoes and vegetables on the table. Potatoes, vegetables on the table. Now I do have to convert my two temperatures. Okay. So I'm going to do that so that I have the correct units to plug in. Okay, I'm just adding 273.15 to my temperatures. Okay. And now we're just going to plug everything in. My initial pressure was 100 kilopascals. My initial volume was 7.50 liters. My initial temperature was 293.15 Kelvin. My secondary pressure was 28 kilopascals. I don't know what my second volume is, that's what we're calculating for, but I do know my second temperature was 237.15 Kelvin. So to get V2 by itself, I need to multiply both sides by 237.15 to cancel out these units. And I need to divide by 28 kilopascals to get rid of this units. All right, so my V2 is going to be 237.15 Kelvin times 100 kilopascals times 7.50 liters all over 28 kilopascals and 293.15 Kelvin. That's going to give me I'm just plugging this into my calculator. And I'm going to report this to two significant figures because three of my numbers only have two. The other three have 3. The other two have 3. So this is going to be 22 liters. Okay. So when the balloon rises, it's going to increase in size to 22 liters from 7.5. Okay. We'll do one more, and then I'll give you time to work on your homework problems. So we have P1 V1 over T1 equals P2 V2 over T2. The question says 500 liters of gas, so this is my initial volume, is prepared at 700 kilopascals. Okay, so this is my initial pressure, and 200 degrees Celsius, this is my initial temperature. The gas is placed under high pressure when the tank cools to 20 degrees Celsius, so this is my secondary temperature, and the pressure of the gas is 30 atmospheres. This is my P2. What's the volume? So we need to figure out what volume is. Now, we do automatically have to convert those two temperatures into kelvins. Okay, so it's going to be 473.15 kelvins, and you also may notice that one of my pressures is given to me in atmospheres and the other pressure is given to me in kilopascals. Those need to be in the same unit, okay? To convert between atmospheres and kilopascals, our kilopascals is going to be our atmospheres times 101.325, okay? Because there's 101.325 kilopascals in 1 atmosphere. So 30 atmospheres needs to be multiplied by 101.325 to get me my number of kilopascals. Okay, so that's going to give me 3039.75 kilopascals. You could also convert the kilopascals into atmospheres. It wouldn't make a difference in your math. Okay, so my initial pressure was 700 kilopascals. My initial volume was 500 liters. My initial temperature was 473.15. My secondary pressure is 3039.75 kilopascals. I don't know what my new volume is, but I do know my new temperature. Okay, so to get V2 by itself, I'm going to multiply both sides by 293.15 Kelvin. Get rid of this unit. Okay, and I'm going to divide by 3039.75 kilopascals. Okay, to get rid of this unit. So my V2 is going to be 293.15 Kelvin times 700 times 500 liters, all divided by 3039.75 kilopascals and 473.15 Kelvin. So that's going to give me plugging that into my calculator. And I'm going to report this too. This has 4 significant figures. This has 4. This has 4. This has 3. This has 3. I'm going to report to 3 significant figures, which is 71.3 liters. Okay, so for your homework for tonight, there's 4 questions out of your textbook. You can try those. Remember, there is an answer key if you're confused. You also can reach out for me for help during office hours or via email, or you can check out our FAQ page where I post solutions for commonly questions that students are having trouble time with. Okay. Other than that, hopefully you are staying safe, staying home, and staying healthy. Looking forward to hopefully seeing you guys soon.